Good afternoon, everyone, and welcome. Thank you very much for coming. I'm Brian Skidmore, and I'm deeply interested in astronomy. And my presentation today is about the astronomy of the James Webb Space Telescope. So no doubt you have seen some of the amazing images that have come down that have been broadcast on the press from the James Webb Space Telescope that are coming to us almost daily. And my presentation is to try and give you an overview of the first years of operation of the telescope, because it's been operating since July 2022. And the focus will be on the astronomy of the images rather than the spacecraft itself so much. But I will start off by introducing the telescope. I'm going to talk for about 50 minutes, and during that time, we'll go through various themes that I have in astronomy that are relevant, that the telescope has been sending us images of. So let me begin by introducing the telescope. So this is the James Webb Space Telescope. Most important part of the telescope is the mirror, which is hexagonal in shape. It's 6.5 meters in diameter. It consists of 18 hexagonal segments, each of which edge to edge is about 1.2 meters, giving a total diameter of 6.5 meters. And that is substantially larger than the Hubble Space Telescope, which is about 2.4 meters in diameter, which gives it more sensitivity. That mirror takes the light from the universe, and I don't know if you can see my mouse, but the mirror focuses the light from the universe onto the secondary mirror, which then reflects it back into the center, in that sort of hole in the center of the main mirror, into the instruments. The science instruments sit behind that, behind the mirror. On top of the mirror sits the mirror sits on top of the sun shield. It's a remarkable sun shield. It's about the size of a tennis court, about 21 meters by 14 meters overall, although it's in the shape of a kite. And it's made of 5 layers of Kapton, which has extremely effective heat-resistant properties. The thermal engineers in the company will be familiar with Kapton, I'm sure. So the telescope has to be kept extremely cool. The science instruments have to be kept extremely cool, because this telescope is not a visible light telescope. It's an infrared telescope. And infrared light is produced by objects that are warm. So all of us in this room are generating ourselves infrared radiation. And so the telescope has to be very cool in order for the body of the telescope itself not to interfere with the observations. So that the shield is oriented such that it faces the sun, and I'll show you that in the next slide. The bottom of the underneath is the hottest part. That will reach temperatures of about 110 degrees centigrade, so higher than the boiling point of water. But the temperature on the upper surface of the top layer will be about minus 220 degrees. So it's extreme temperature difference of about 330 degrees, keeping the telescope extremely cold. And the mirror itself is made of beryllium, a very light metal, which has very good properties, very light and excellent properties at cryogenic temperatures. So that, in summary, is the telescope. The power and the bus are underneath the spacecraft. We can't really see that in this image. And this is an animation that will show you where the spacecraft is with respect to Earth and how it orbits the sun. This will work. So you can see that the spacecraft is orbiting in a circle behind the Earth. That circle is called a halo orbit, and the center of that halo orbit is an object in space called L2. And as you can see in this animation, L2 co-orbits with the Earth, and lies in an opposite direction to the Earth from the direction of the sun. It's about 1.3 million kilometers away. And other spacecraft do this as well. And this has the advantage that if compared to orbiting the Earth, it means that observations are not eclipsed by the sun. It also means that the telescope does not see infrared light from the Earth, because it's seeing the far side of the Earth. So it will see a tiny amount, but much less than if sunlight was bouncing off the Earth. So it never sees sunlight reflected off the Earth. And it also means that the telescope keeps a constant distance from the Earth, which helps from a a power budget and a data rate point of view. So this is what physicists and astronomers refer to as the electromagnetic spectrum. I'm sure that many of you have seen this before. And it's just a diagram that illustrates the different kinds of light, the different wavelengths of light that nature produces. And so visible light is that tiny fraction of that ultraviolet, that electromagnetic spectrum that we can see with our eyes. And it's from 0.7 to 0.7 microns, where a micron is a millionth of a millimeter. And as I mentioned, the James Webb Space Telescope is observing at longer wavelengths. And there are important reasons for that, which I will touch upon in the presentation. But the primary reason is because James Webb, the motivation for James Webb is to see the earlier structures in the universe that were formed near the beginning of the universe. And although at the time they would have been in the ultraviolet produced by massive stars, the expansion of the universe since, by over a factor of about 1,080, has stretched the wavelengths into the infrared region. So that in order to see those, you need an infrared telescope. And you need to go really into space because the atmosphere, the absorption of the atmosphere is represented by this grey filled-in curve above the black line, illustrates where the atmosphere is opaque. So you can see that in visible, it's not opaque as long as it's not cloudy. But in infrared, there's a lot of opacity, and it's certainly opaque in microwaves and X-rays and beyond. But for James Webb, the important point is that there's a lot of atmospheric absorption in the infrared. So to go above the atmosphere has tremendous advantages. Although there are infrared telescopes on the Earth, but they're up high mountains to get away from as much of the atmosphere as possible. So I'm not going to go too much into the instruments because I'm certainly not an expert on them, and I haven't researched them in detail. But there are 4 instruments on the taking science data. There are 3 in the near infrared, represented by the left-hand side of the diagram. So on this diagram, you have the visible spectrum from about 0.4 to 0.7 microns. And the 3 of the instruments on JWST are slightly within the visible region, but mostly within the infrared, up to 5 microns. There's what are called the near infrared instruments, near spec, a spectrometer, near camera, and nearest, which isn't mentioned so much, but is a near infrared image. It's sort of a combination of the two, of a spectrograph and a camera. And then you have the mid-infrared instrument on the right-hand side, which looks at medium infrared wavelengths. And I'll illustrate another reason why this is useful for physicists and astronomers. So this is an image from the Hubble Space Telescope in visible light of the pillars of creation. This was the name given by the media to a particular area called the Eagle Nebula. And like all nebula, it consists of gas and dust. In fact, the word nebula means cloud-like, out of which stars are forming. Now, in this image, you can see that not only is there a great deal of dust, but also that much of it is very opaque because it's in the visible region. And in the visible light, dust will absorb radiation. Dust will absorb the light from the stars, and so it's pretty much opaque. And what astronomers want to do is lift the veil of that gas and look in the infrared. So if you look in the near infrared, and this is an image from JWST, you see this, which is very different to this. Suddenly, you really are I'm blown away by the impressive image that have come from JWST. So first of all, you see far more stars, lower mass stars that are shining in the infrared that you don't pick up in the visible. You also see there is a greater resolution at this frequency from JWST, although not so much at longer frequencies. But importantly, the dust, although it is opaque, it is more translucent, and in detail you can see more. Incidentally, the sort of red areas at the top are where iron is present, but I have other images to go into. This is just illustrating the effectiveness of near infrared observations from James Webb. Now, in the medium infrared, longer wavelengths, then that's also useful because although you're seeing far less stars, what happens is that the dust re-radiates in the medium infrared wavelengths the light from the stars that are forming within. So that means that if you are interested in dust, and some astronomers are interested, many astronomers are interested in dust, because dust is the material from which everything comes, stars and planets and solar systems, then you can see the detail in the dust because it's in medium wavelengths, infrared wavelengths. The dust is being re-radiated, so you can see far more detail in the dust here than you can in the Hubble image. Yeah, so if you're interested in dust and star formation, you've got the best of both worlds with James Webb, more translucent dust and dust structure and detail in this image. So moving on, this is the first of four or five themes that I have. This theme is star formation. And what I'm going to start with is an animation produced by NASA. This image is not from James Webb. It's a wide field image. And the animation will start with this image. We see the galaxy, the Milky Way galaxy on the lower left, and the great dust lanes. The bright star there is Antares. And what it's going to illustrate are the two constellations that are in that region. We have Scorpius and Ophiuchus, and then we're going to end up an image from James Webb of the star-forming region Rho Ophiuchi. Rho Ophiuchi is just the name of a star in the constellation of Ophiuchus. Let's hope this works. So this is the animation, and I'll just let you enjoy this as we take a journey to a Rho Ophiuchus complex. And so we've arrived rather smoothly with the magic of animation onto this beautiful image that was released by the James Webb Telescope team back in July of this year to celebrate 1 year of operations. So what I should have mentioned was that the telescope was launched on Christmas Day 2021 and began its science about 6 or 7 months later in July of 2022. So this was released in July of 2023. And what we're seeing here is a star-forming region called Rho Ophiuchus. Rho Ophiuchus complex, I should say, and that consists of many regions of gas and dust from which stars are forming. And it's a small cluster of stars, about 50. Most of them are about the mass of the sun. And it's the closest star-forming region to Earth. It's about 390 light years away, which is a vast distance on human scales, but it's very close in galactic terms. Just to say that a light year is the distance that light travels in a year, not a unit of time, and it's about 9.5 trillion kilometers. Anyway, so I'm going to focus now on the lower left. Oh no, I'm not. Yep, so here we go. So NASA had a rather wonderful term for this. It referred to it as this impressionistic texture. So the first thing that is, I think, rather beautiful is the texture that you see. This level of texture at this wavelength has never been seen before. But from a scientific point of view, you're looking at a star that is the most massive in this complex, referred to as S1. It's more massive than the sun, and it's massive enough to produce ultraviolet radiation. And what that does is that it causes the surrounding gas to glow, because it's exciting the electrons in that gas to higher energy levels, which then cascade down and emit particular frequencies of light. But it also has a powerful wind of elementary particles, which are causing a sort of cave to be formed in the gas around the star. Also, what astronomers see here is emission from a molecule called PAHs, polycyclic aromatic hydrocarbons. These are a sort of matrix. The molecules are sort of many rings, carbon-containing rings of molecules joined together, atoms all joined together. These are common on Earth, but it's thought to be one of the main mechanisms of the way that carbon is being incorporated into the Earth and its formation. So PAHs are a common theme in star formation, but a very interesting one for astronomers. So stepping back to the original image, in the upper right of that yellow area is a dark, dusty area, and inside there, a star is forming. And those dramatic red jets that we see to the upper, about 11 o'clock, and on the opposite corner, opposite side, about 4 o'clock, are the jets from a star that is forming there. So what I've done is I've taken this graphic to illustrate what is happening inside that cloud. So a star is forming. These stars are very young. A new star is forming right now, and it is thought to be surrounded by an accretion disk, because as it gathers gas and dust, it will begin to spin, and around its equator, it will gather this gas and dust. This is a common theme in star formation, and also you get these accretion disks around white dwarfs, neutron stars, and black hole stars at the end of their lives. And so this material will spin, and gravity will attract it to the star, and this is the material from which the star is made. But much of the material is moving too fast. So what happens is that magnetic fields around the star funnel these into the dramatic jets that we see either side in red. These are molecular outflows, bipolar outflows. So when you see those outflows, they are occurring from the poles of the star that is being formed. And astronomers have never seen the detail that we see here in those outflows. They're really dramatic, I think very beautiful. We can see them just to see. And the level of detail, the translucence, is extremely impressive. And lastly, I want to focus in on 3 stars. I'm highlighting them here in formation in this gas cloud. These are new solar systems that are being formed further away in the cluster. You can see impressive shadows here, either side of this star, cast by the accretion disk around it, which is occupying a much smaller area. And you can see shadows here as well. So these are brand new solar systems, sort of pregnant with potential, if you like, for forming planets, and who knows, perhaps forming stars. So the next theme I want to look at is the death of stars. So stars can die, very massive stars die in very dramatic ways called supernovae, but less massive stars, which are more common, such as the sun, die in the following way. So this is an image from JWST. This is the Ring Nebula. Amateur astronomers will be familiar with this nebula because you can see it in a medium power telescope, 6 to 8 inches. There's a very faint ring in the constellation Lyra the Lyre, but you certainly can't see it in this level of detail. And what's happening here is that the star in the center, we'll zoom in a moment, has reached the end of its life. And prior to the fairly recently, it was a red giant. So what happens is when a star is living its life, it is burning hydrogen, because stars are primarily made of hydrogen. It is consuming hydrogen and converting that into helium via nuclear fusion in its center. At the same time, gravity is trying to compress the outer layers of the star, because gravity is always attractive. And so the star in its adult life is a balance between these nuclear reactions and the pressure of the gas of the star. And this is true of the sun, it's true of all stars through their adult life. So at the end of its life, a star will run out of hydrogen in its core. The core will then contract due to gravity. That will push up the temperature and pressure inside the core, and it will then start to fuse helium. Helium for stars that are sufficiently massive, but this will include the sun. And helium will then be converted to carbon and oxygen. And then there will be no further reactions for stars of this sort of mass about the size of the sun. So, and then when helium burning is much more powerful than hydrogen burning, it's much shorter, and it's powerful enough to blow away the outer layer of the star. And that's what you're seeing here, the outer layer of the star. It's actually barrel-shaped. It looks two-dimensional, but it's actually sort of barrel-shaped. And the star responsible is the one right in the center. It's actually shining predominantly in ultraviolet, and it's a temperature of about 120,000 degrees centigrade, far hotter than the outer surface of the star when it was a normal star. And that's because the helium reactions have heated that core to that huge temperature. And it's now cooling off, and it will cool off for billions of years. And that tremendous temperature produces ultraviolet radiation, which lights up lights up much of the nebula. So if we look in the outer parts of the ring, we see these globules of hydrogen. This is what has been determined by spectroscopy. There are 20,000 of these in this inner ring. seen in detail, never been seen before. If we go to the opposite side, we can see these characteristic stripes that are radial, pointing away from the center. These are thought to be where molecules are being able to form because they are being in the shadows of globules inside of the ring, which are causing shadows from the inner ultraviolet radiation, causing molecules to form in their shadow. So you get all these tremendous stripes. So that was a near-infrared image. And if we go to a mid-infrared image, we can see these tremendous concentric circles. And you wouldn't expect that if this was a single star. So what is thought to be happening is that there is a binary star. It's in orbit with another star, which has an orbit of about 280 years. And so we get these concentric rings every 280 years. So this thing is expanding tens of kilometers per second, still expanding. It's about 7,000 years old, 2,000 light years away. And astronomers can actually see this. It's expanding about 1 arcsecond in angle per year. So let's go closer to home. The James Webb Space Telescope has imaged the gas giants of the solar system, and I will only mention Jupiter and Saturn, but also 2 of the moons of Jupiter. It's also looking at Kuiper Belt objects much further out. It cannot image inside the orbit of the Earth and the inner planets because they are too close in angle to the sun. So it's prevented from doing that. So this is a beautiful image in the infrared, of course, of Jupiter. It is taken in 3 different frequencies, with the longest frequency illustrated in red. Now, what I meant to mention at the beginning but forgot is that all the colors that you see in this image and all the other images that I'll show are artificial because the light is not from the visible spectrum. They are put there by whoever created this image. See, this is just data and the different frequencies are colored. They're normally colored, the longer frequencies are normally colored red and the shorter frequencies colored blue, although not necessarily the case. That doesn't detract from their power and it doesn't detract from their scientific value because astronomers are really looking at the underlying frequencies, but it is important when you're looking at these images to know that. So we see here aurora in red at the poles, the magnetic poles of Jupiter. Jupiter has a tremendous magnetic field and it interacts with particles from the sun, the elementary particles from the sun in the solar wind, which blow continuously. They are charged, consisting of hydrogen and higher nuclei, positive nuclei, as well as electrons, negative. And these electrons spiral around the magnetic field lines of Jupiter onto the magnetic poles of Jupiter. They then ionize the atmosphere and cause it to glow. And that's what you're seeing here, very similar to what's happening on Earth, but on a much larger scale. When we're talking about scale, this is the great red spot, well, it's red in visible wavelengths, and this is about the size of the Earth. So you can see how vast the planet is, the biggest planet in the solar system, 140,000 kilometers in diameter. In green, we see hazes around the poles, and in white, we see hazes that are reflected from clouds from hazes, aerosol particles, that are hundreds of kilometers above the features that you see here. So what isn't really clear is that actually the atmosphere is very deep. There is no solid surface. This is a gas giant, and the atmosphere simply gets more and more dense as you go further down. But there are complex layers of clouds in the top several hundred kilometers, consisting of ammonia and ammonium sulfide. And what these So that, as I say, the white is showing the high hazes, and the blue, the various shades of blue are different depths, with the darker blue at different depths. So there isn't really a take-home scientific result yet from these images, but it is extremely impressive, and scientists are working hard on interpreting this complex data. And no doubt there will be papers in the future. And if I zoom in, I can just show you some of the exquisite resolution that James Webb is showing. This is very dynamic. It's constantly moving, eddies, orbs pop in and out of existence continuously, except the great red spot, which has been around for several centuries, although it is shrinking. So this is often people's favorite planet, Saturn, of course, with its exquisite rings. And the rings are very bright. This is about 3.5 microns, I believe. The planet has never been imaged in such detail at this frequency. The atmosphere is very muted and it's very dark because the atmosphere is made of methane. There's a lot of methane, rather. It's predominantly hydrogen and helium, but there's much methane in the atmosphere, and it absorbs infrared light very well. So that's why it's much duller than the rings, which are extremely bright because they're made of ice particles, millions and millions of them. So again, not obviously a take-home scientific message at the moment, but scientists are trying to work out why the reason for this darker, this attenuation around the North Pole of Saturn. You can see Dione, Enceladus, and Tethys here. We'll talk about Enceladus in a moment, and the various rings that have been well catalogued. A great, over the centuries they've been catalogued as they've been discovered, with the Cassini division and the gap, which are gaps in the rings caused by shepherd moons that you can't see in this image, but exist in the Saturnian system. But this is a very well-studied system. The Cassini mission, which I talked about in 2020, has extensively explored the system already, and indeed passed through the Cassini gap. But it's a beautiful image, I think you'll agree. Moving on to Titan, which is the largest moon of Saturn, and indeed I think it's the second largest moon in the solar system. As I mentioned just now, I gave a talk specifically on Titan in 2020. Some of you may remember. It's an extraordinary world. It has a very substantial atmosphere, more substantial than that of the Earth, would you believe? Even though it's a moon, it's much smaller than the Earth. It's comparable to the size of Mercury. It is the only body in the solar system, apart from the Earth, which has standing liquid on its surface. But it's not liquid, it's hydrocarbons, because it's so much carbon. It has a hydrological cycle, not of water, but hydrocarbons. It has clouds. Would you believe it? It has rivers, it has deltas, it has seas, it has lakes. It's an incredible world. It's like a very low temperature version of the Earth. And what you see here are data in the infrared colored to accentuate different features. On the left, we have the lower atmosphere and clouds. And on the right, we see clouds, but also atmospheric, also surface features. Bellet is a sand dune. Bellet is a sand dune. Addery is a region of high brightness, and Kraken Mare is a sea of hydrocarbons, methane predominantly, I believe. The clouds are highlighted because that's what the astronomers were excited about when they saw this image, because clouds and cloud changes over time. This was followed also by the Keck telescope on the ground, which does have an infrared camera, followed the clouds, and that can tell astronomers a great deal about the dynamics of the atmosphere. I'm not a meteorologist myself, but it is very useful. So that's Titan. Here we have another moon of Saturn, a very exciting moon called Enceladus, much smaller than Titan. It's about the diameter of Norfolk, 250 kilometers. It's exciting because it is certain that it has an undersurface ocean. So it has hydrothermal vents because previous mission Cassini detected some salts in the plume. It passed through the plume. So it has not only an underwater ocean, but actually it's jetting that ocean to space continuously from its south pole. And what Webb has discovered is a giant, because it was able to take a wider field, it realized that these jets were actually extending, I think, 2,000 kilometers into space. So that's very exciting, and it means that hopefully spectroscopy from James Webb will discover other molecules or atoms in that plume. Unfortunately, in this campaign, it only discovered water, even though Cassini, which flew through it, discovered some ionic compounds. So this is just a graphic which illustrates the structure of Enceladus, or what the structure is thought to be, with an inner rocky core and an outer icy crust which are disconnected from each other. And the Cassini mission was able to establish that was the case because of the shifting gravitational center. And between the two is thought to be this ocean, and there's direct evidence from these jets. One of the mysteries is why is the liquid inside Enceladus actually not frozen, because the moon is so small. It should be losing heat, but it's undoubtedly heated by its orbit and the presence of other moons. But it's still a bit of a mystery. This is an image from James Webb on several frequencies of the planet Uranus. Uranus is bizarre because it actually is tilted almost 90 degrees. So instead of orbit, so it sort of rolls around the sun. So if you think of the poles as almost in the plane of the orbit and a constant direction, it's sort of rolling around the sun like this. One of the most striking things, if you're familiar with the rings of the solar system, is that the rings of Saturn are extremely clear in almost any amateur telescope, but no amateur telescope will show you the rings of Uranus. They're very dark, and in fact, I don't think they were even discovered until 1980, and only then because the rings passed in front of a star which winked 5 times on one side and then winked 5 times again on the other side. So there must have been a symmetrical structure around the planet, which were confirmed to be rings later, and they were observed by Voyager 2 as it flew past Uranus in 1986. So there's a great deal of detail here in the rings that can be seen. You can also see there's a bright cloud. This is the North Polar Cap. This is clouds here. And in invisible light, this is actually almost featureless. So you can see more in infrared. And these clouds are characteristic of the storm features that infrared wavelengths are revealing. The system has about 47 moons at least, and they're all orbiting in the same plane as the rings, or which is in the same plane as its equator. So they are all orbiting on their side as well, as it were. Okay, so now we're going to move on to the fourth theme, which is exoplanets. And exoplanets are planets orbit other stars. And in fact, today is very nearly the 5th anniversary of my exoplanets talk that I gave back in 2018. Anyway, so with that, about many more exoplanets have been discovered since those days. I think it was about 2000. Now it's about 5,500, which is extraordinary. And this is tremendously exciting because what we want to do is find a planet that we think hosts life, that is like the Earth, and it's a journey. And JWST will take us on that journey further than we've gone before, but we're not there yet. And I've picked up 4 planets. I will need to pick up pace a little bit because anyway. So what I'm going to show you first of all is an animation, and the animation will illustrate how planets will be discovered by JWST or studied by JWST. JWST isn't primarily a discovery machine. Other missions will suggest or think they've discovered planets and then pass those candidates to JWST to try and confirm in some cases. So what you'll see is an illustration of the so-called transit method, and it will begin with a planet moving around a star from above, and then the animation will tilt so that you see the planet moving in front of the star. And I'll start it now. So the planet is moving around the star in this illustration. It happens to be a circular orbit, and if we are looking at the star such that the planet does in fact pass in front of the star, the total light from that star will dip in a characteristic way, as illustrated by this light curve shown on the bottom left. And it is harder than it sounds because there's a lot of the star is not a constant source necessarily. It will fluctuate, so you have to have a very sensitive instrument. And it's important to say that the telescope does not see what you see in that animation. It only sees the light from the point of the star. Virtually every star in the universe is just a point source, even to the most powerful telescopes. There are exceptions like Betelgeuse, but generally speaking, that's not the case. So telescope is looking for that dip. And from that dip, it can establish the size of the planet relative to the star. You still need to know the size of the star to get the size of the planet. And that is very helpful. But there's other things it can do as well. So I'll illustrate. So this is one of 5,500. That I've selected, and this is the first one studied by JWST. It happens to be called WASP 39b, and it's characterized as a hot Jupiter. So it's called a hot Jupiter because it's a Jupiter, roughly a Jupiter-sized object, about 30% larger, but it's right next to its star. And this is a bizarre finding that was true actually from the very first exoplanet discovered back in 1995. So that in itself is not a discovery of JWST. What JWST is doing is taking a spectrum of the planet and a spectrum of the star and subtracting them to find out the spectrum of its atmosphere. So this has a relatively large atmosphere because it's a red giant. It's a Jupiter. It's a gas giant. Nevertheless, it's still an extraordinary achievement. And what the telescope does is that it takes that, it calculates that spectrum from a subtraction of the two spectra to produce this. And this is called a transmission spectrum. Essentially it's the absorption of the light from the star that is being absorbed by the atmosphere of the planet. And that, if you spread that light using the near spec, yes, it's a near spec, and mirror is probably involved as well, then you end up with a spectrum. A lot of processing involved in modeling. And so the data points are the diamonds in white, and the model, the complexity comes in deriving the model and fitting the points, is in blue. And you can see excellent agreement with the detection of sodium and water, carbon monoxide, sulfur dioxide, phosphorus dioxide, I think is there too. So sorry, it's just not phosphorus dioxide, sulfur dioxide. So what JWST has managed to detect carbon dioxide. This is the first planet where carbon dioxide has been detected. Water had already been detected, and sodium by the Hubble Space Telescope. But carbon dioxide is a new discovery by James Webb, and it's the first planet to have sulfur dioxide detected due to photochemistry. So photochemistry is when the light from the star breaks apart molecules in the upper atmosphere and creates new molecules. This happens on the Earth with oxygen and ozone. And so that's interesting as well. So new discoveries. And what's important about infrared is that many molecules, such as methane and water, have many absorb in the infrared significantly. And if you can only look in the visible, then you can't really tell the difference between water and methane. It's only when you go in the infrared that you can tell the difference. And so that's another reason why infrared is important. Moving on to another planet, this is LHS 475b, a very different planet. This is a terrestrial planet, a planet with a solid surface. And it is very, very similar in size to the Earth, but it's unlikely to host life because it is very close to its star. It's only a 16th of the distance from its star that Mercury is from our star. So it is being very powerfully irradiated by its star, although its star is a much smaller mass star than our star. So the calculation of the temperature is about 313 degrees centigrade, so distinctly uncomfortable. So they did try, and it has a very short period. It whips around its star every 2 days. And this is the spectrum that's been taken from the planet. And really what I'm showing you here is that not every spectrum will produce exciting results. So actually, this is really a null result. None of the models fit the data, and the data is very noisy. And the reason for that is that the planet is very small. So the layer of atmosphere that the spectrum is deduced from is extremely tiny compared to a gas giant, which has a much larger atmosphere. Also, my view is that it almost certainly doesn't have an atmosphere. But apparently the authors think this is consistent with the carbon dioxide atmosphere, but they only think that because it's the size of Venus, and Venus in our solar system has a very substantial carbon dioxide atmosphere.
Sorry, these spectrums, we realized about, I probably got it wrong.
No,
that is spectrum taken from the light reflected off the planet through the atmosphere.
It's not reflected in this case, it's transmitted through the atmosphere.
Around the side.
Yes.
Okay.
So if you imagine the planet, if you imagine a cross section, you have the disk of the solid planet, and then you have the atmosphere as an annulus around it. I should have had a diagram really. And the light is filtered through that annulus. So you can take a spectrum of the star directly at any time. When the planet is in front of the star, you can see that because of the overall dip in light. You can take the spectrum of the star again, and that's the spectrum of the star plus being filtered through the atmosphere.
So thinking this light reflected off the planet obviously also goes through the atmosphere, so must have that data in it. But okay, that's how it's done. I was just wondering.
No, because the light reflector will go back to the star. but you can get light reflected when the planet is the other side. Oh yeah, that's true. You can, yes, you can when the planet is the other side. You're quite right. Yes.
Well, I mean, that's not how it works.
So for this, it's when the planet is in front of the star. There are other measurements for this one actually when the planet is next to the star, when it's rotated, and you can measure actually for a different planet how bright it is. But we can talk about that afterwards if you like. So what we're really illustrating here is that we're showing the limits really of Webb for monitoring for measuring the spectrum of this particular planet. But for other terrestrial planets, it may be better under more favorable conditions, especially if the thing actually has an atmosphere. I suspect this doesn't have an atmosphere, which is why the data is so noisy. But sometimes null results are important to characterize the instrument and to show where the boundaries of its capabilities lie. So this one caused a great deal of excitement very recently in the press. So this is, of course, a graphic. It's not an image from JWST. And what the authors of the paper who behind this characterize it as a water world, it is almost certainly not a water world. So they suggested that actually it had a solid surface and it had a global ocean, and that meant that was consistent with the diameter and the mass of the planet. The mass was determined by other measures. So what James Webb can give you is the diameter. Other instruments, mainly on the Earth, can give you the radius in certain cases. That was the case with this planet. Therefore, we know its overall density because we know how big it is and how heavy it is. And there are lots of models of a given planet that can fit that data. It won't give you the exact composition. And one possibility is that it has a global ocean with a hydrogen atmosphere. In reality, it's too large, really, to be a water world, unfortunately. It actually has, because it has a radius of 2.6 times that of the Earth, the sort of crossover point for terrestrial planets is thought to be 1.5 times the mass of the Earth, the diameter of the Earth. And because it's much larger than that, it's much more likely to be like Neptune rather than like a water world, what we call a super Earth. So unfortunately, it's unlikely to be what the authors suggest it is. And the press got excited because of the spectrum, because the authors claim that they've discovered dimethyl sulfide, which is the third from the right. I'm not sure why my mouse isn't showing. And that is exciting because on Earth that is only produced by life. In the natural world, I mean, it can be produced industrially, but it's only in the natural world produced by life. But in fact, if that were true, that discovery, it would have to be an enormous amount of dimethyl sulfide in the atmosphere, and that certainly isn't true on Earth. But also, it probably isn't there. It was only discovered at a significance of 1 or 2 sigma, I think 1 sigma, which means there's actually a reasonable probability that it's just chance, and it actually came from the processing chain to produce the spectrum. So the only group that think it is dimethyl sulfide, there's only one group, and it needs testing by the group. So I'm skeptical. Other people actually are skeptical that that's true. And moreover, they didn't discover water. Earlier measurements by the Hubble Space Telescope did show water, but in this one, didn't show water. I am going to skip ahead faster to make sure that I keep within time. So this is what's called a direct imaging of a planet. So if a planet is sufficiently massive and sufficiently young, that means that it can be very brighter compared to its host star than other planets. And that means that it's a candidate for being imaged directly. And this is one of them. This is 65426b, which has been imaged directly by JWST. Unfortunately, you don't see a beautiful image of the planet. You just see this sort of what's been called a hamburger at various wavelengths. And the star is where the star actually is. And it's been blocked out by a coronagraph on the telescope, which has blocked out that star. It's very difficult to do this. It takes a lot of processing. And the hamburger shape is an artifact of that processing to bring up the contrast of the planet. It's not real. So it's interesting. It's a very massive planet. It's about 7 times the mass of Jupiter. And it's very large, about 1.5 times the size of Jupiter. It's on the boundary, actually, of being almost a star. But it illustrates the capability of JWST. So JWST will keep going probably for 20 or 25 years. And this is really an experiment to show what it's capable of. So there isn't science really from this image. So this is my final theme, the early universe. And as I said at the beginning, the primary motive for the telescope is to look at the early universe, to see the first structures forming. Because although at the time they would have been in the ultraviolet, I'll illustrate this in this diagram, and this is similar to the diagram that I showed last Christmas in my cosmology talk. So what we're seeing here is that time is along the x-axis and the beginning of the universe is on the extreme left, and you see that on the diagram. So the various diameters of this are the relative size. It's a confrontation. It's a controversial thing to say size, but the relative expansion factor of the universe since the beginning. And so at the beginning, there was thought to be this tremendous expansion of inflation. And then the universe continued expanding at a much slower pace. And that occurred about the beginning was 13.8 billion years ago. That's pretty much a consensus on that date. But the universe began in a very hot and dense state, too hot for atoms to exist. Instead, you had a soup of elementary particles, many of them charged, so light was being continuously generated and then reabsorbed by those particles. And as the universe expanded, it cooled. And about 376,000 years after the beginning, you see that colored disk. That is the point at which the atoms first began to form. Neutral atoms, where protons are combining with electrons to form neutral atoms, primarily of hydrogen, but a bit of helium and lithium. And that meant that the universe was then transparent to light, and light could then freely stream through the universe. But stars then formed from that material. Normal matter, but also dark matter, most people think, most astronomers think, to form the structures of the universe. And that's what we see represented by these disks. Oh, sorry, I've gone back. These disks. So these disks are really the forming structures. And what JWST is to see far back as possible into what are called labeled the dark ages. That's where the neutral atoms are beginning to form stars and planets, stars primarily. And those stars are thought to be very massive, producing a great deal of ultraviolet, high frequency radiation, electromagnetic radiation. And we need, as I mentioned, we need an infrared telescope because the expansion of the universe has stretched those wavelengths to infrared. Now, that's called reionization because those ultraviolet stars and also galaxies that are forming reionize the gas around them. So that's why it's called reionization. And then we end up with the universe that we have today. But astronomers want to see the earliest galaxies, the earliest stars, also the earliest black holes, but that's not included in my talk today to keep it manageable. So this on the right, so this is an image on an area of the sky called sorry, I beg your pardon. This is the JWST deep field image. It's about 12 hours. On the right-hand side is JWST. On the left-hand side, you would see the same area of the sky imaged by the Hubble Space Telescope. And so on the right, you see far more galaxies. And it was the image that was presented by President Joe Biden to illustrate the great power of the telescope. And at the time, it was the deepest and most precise image of the deep universe ever taken. And in the next slide, I'm going to show it in more detail. So you see, it's exquisitely beautiful. There are thousands and thousands of galaxies. Now, in fact, there is a foreground galaxy cluster shown mainly in white, and the back there are much more distant galaxies, which are more illustrated in red, longer wavelengths. Remember, these colors are artificial. This is infrared, and we can zoom in and just admire the quality and the beauty of this image. And there's nothing I can say really that can illustrate just how beautiful this is and how extraordinary it is. And I'm just panning across to just show you the width of it. And you can zoom in, and if you're on Teams, you can actually zoom in yourself. If you hit the control button and wheel your mouse, you can zoom in. And of course, you can do this online as well. But what you're also seeing are distorted images, and that's because, so this distorted arcs that you see are caused because the central white galaxies are actually form collectively a significant gravitational collection, and general relativity predicts, and it's true, that will bend the light of the foreground galaxies around that cluster and distort them into the arcs, but it will also magnify them, which means that we can use gravitational lenses, they're called, to see much further back into the universe. And this is another one. This is the JADES. JADE stands for JWST, Advanced Deep Extragalactic Survey Area, that was imaged by JWST. There are 45,000 galaxies in this image, and it subtends, the angle it subtends is equivalent to holding a grain of sand at arm's length. So the universe is absolutely teeming, and astronomers are finding more galaxies than they expected. They are also finding that galaxies are more mature than they expected at the earliest times. This is just to allow you to admire this extraordinary image. So the furthest galaxies will be much smaller than our galaxy. But you can see that many of them have formed disks and gas, but they still contain hundreds of thousands to millions of stars. It's just extremely beautiful. So this is Maisie's galaxy. It's called Maisie. This is one of the furthest galaxies ever discovered, and I wanted to illustrate it because it's developed sort of iconic status. It was called Maisie's galaxy because the last but one author here, Steve Finkelstein, was the leader of this study, and his daughter, when they discovered this galaxy, it was his daughter's birthday. I think she was 9 or 12 or something, and so they called it Maisie's galaxy in the group, and then it gathered momentum, and it was actually in the published paper. It's called Maisie's galaxy as well. So let it not be said that astronomers don't have feelings too. This is Maisie's galaxy, and you can see, I mean, not a great deal is known, but clearly it's not a mature disk galaxy. It is yet to mature into a disk galaxy, and it has a redshift, which is if you use spectroscopy particularly, you can measure this by something called the Lyman alpha break. I won't go into that. The redshift of this accurately, and it's been determined to have an enormous redshift of 11.4. And if you're not used to the numbers, that won't necessarily mean much, but that translates into about 390 million years from the beginning. Now, that sounds like a long time, but when you remember that the universe is 13,800 million years ago, that's a fraction of a percentage. So we're seeing right back to the earliest times. There are galaxies that are even earlier than that. This is to illustrate, really, and I'm drawing to a close in a moment, but 100 years ago, it's exactly a century ago since Edwin Hubble, after whom the Hubble Space Telescope is named, discovered the expansion of the universe with others. I must say there were others involved, but also he classified galaxies, and that classification, broadly speaking, consists of roundish galaxies, which are called elliptical galaxies, which are sort of amorphous collections of stars, and disk galaxies, which have this beautiful disk-like structure. Many of them have spiral arms, including our own galaxy. And it's thought that the elliptical galaxies are actually the result of collisions of spiral galaxies, disk galaxies. And what I'm illustrating here is that with James Webb and also Hubble, it's been discovered that this classification holds back all the way to about 11 billion years. So that's quite interesting. So you're getting galaxies maturing into these basic classifications pretty early on, earlier than expected. But before that, James Webb has revealed that there are signs of galaxies beginning to, in the process of maturing. And so you see galaxies here which are hard to classify. Some of them clearly have a disk. Others are sort of more ragged. Some of them emerging close. Galaxies were closer together in those times. So we're beginning to penetrate into the beginning of these structures, but we're not there yet. Astronomers have realized that they tend to be brighter than expected, and they get more mature galaxies than they expect. And this is to end with an animation of that NASA's put together of that previous image, but with the known distances of the galaxies mapped in 3D so we can fly through them. And we end up actually at Maisie's galaxy, which is quite nice. I thought this would be a nice way to end the talk. to now moving to the outer reaches of the universe, culminating in the latest galaxy.
Lots of tiny galaxies all by themselves.
Yeah, some of that. Yeah, it's just the ones that have been observed rather
Yeah.
than a comprehensive collection of galaxies.
There's going to be billions of times the speed of light that you're flying.
Yes, absolutely. You couldn't possibly do this. Absolutely. Yeah. I think billions is an underestimate, actually. So, this is my conclusion slide, really. So, James Webb is a phenomenal achievement. It's a significant stepping stone in our understanding of the early universe. It will give us more information on the beginnings of the universe. It will detect more molecules in the atmospheres of exoplanets. It will reveal star formation in a way that we've never seen before and is already doing so. It will do so many things. It's a general purpose instrument. Astronomers are spellbound by its capabilities. In fact, there are cycles. So there are cycles of observation that each last a year. We're in the second cycle of observation now. Proposals were submitted a year ago, and the telescope is 7 times oversubscribed. So if you submit a proposal, you've only got a fraction of a chance of actually getting it accepted. So the astronomical community is just amazed, and the public alike. I mean, these images, I think you'll agree, are really astounding and beautiful. And of course, it will discover things that we don't know, we can't anticipate. So 20,000 people, 20 years in development. The first idea for it was in 1988. So actually it goes back 35 years before Hubble. $10 billion budget. It's a beacon of human achievement. An extraordinary telescope, which is revealing the awe of the universe. That's it. Thank you very much.